Okay, so in order to make Simpson's rule work, in other words, we want the integral to be exact for quadratics, like we mentioned earlier. It needs to be exact for this function. Really, it means any constant. f2 of x is f2 of x equals x, f3 of x equals x squared. If we can make it exact for those three functions, we've made it exact for every quadratic there is, because every quadratic is a linear combination of these three functions. Just put a number in front of each one of those. It could be 0, but every quadratic is a linear combination of these three functions. As we would say in linear algebra, these three functions form a basis for all quadratics, because any linear combination of them, or every quadratic, is a linear combination of those three functions. So, without loss of generality, let's assume that a is -1 and b is 1. So our midpoint will be 0. So our area of f under f1 is, let's see, that's the integral of 1 dx from -1 to 1. That's going to give us a 2. If you integrate that, well, maybe I'll go ahead and put x from -1 to 1, and that's equal to 2. The second function is the integral of x dx from -1 to 1, and that's x squared over 2 from -1 to 1. That's going to cancel out and give us a 0. And the third function is x squared. So from -1 to 1, x squared dx, which would be x cubed over 3, evaluated from -1 to 1, and that's going to give us a 2/3. So, I'm going to erase the board, but we need to remember these three numbers, 2, 0, and 2/3. The area of the constant function 1, area under x, and the area under x squared. All right, so in order to ensure that that linear combination works for all quadratics, we need to ensure that the areas are exact for all linear combinations of those three functions, f1, f2, f3. So we will force the following. We're going to force this matrix, which will be f1 of -1, f2 of -1, f3 of -1, as I go down the first column. In the second column, we'll just be replacing the -1s with 0s. You didn't know we were going to be doing linear algebra. Oops, that's f3 there. f1, 2, 3, 1, 2, 3, f1, 2, 1, f3 of 1. Times 3 variables, which I'll call a, b, and c, are equal to the numbers that we had on the previous board. It was 2, 0, and 2/3. We need to find the a and b and c that will make it work. And remember what this is. This is just saying that the particular linear combination of these three values that's going to give us a 2 is a times this one, b times this one, and c times this one. Add them up, we get 2. But on this row, we'd have a times this one, b times this one, c times this one, giving us 0, and likewise on, on the third row. So let's see, I guess I should solve that. So this matrix is actually pretty simple. Right here, we just plug it into the functions on the previous board. That would give us this. Times ABC. Yeah, I'll write it all out. ABC is equal to 2, 0, 2/3. So then if we were to do elimination on that, I'm going to have to rewrite that. 1, 1, 1, 2. Negative 1, 0, 1, 0. 1, 0, 1, 2/3. I just need to solve that system of equations to find out what A, B, and C are. So this would be my augmented matrix. All I would need to do to make this a lower triangular matrix using Gaussian elimination is I'd say row 2 plus row 1, and this would be row 3 minus row 1, and that would give me 0 here, 0 here, and that'll do it, I think. Let's see, the top row stays the same. The next row, when I'm adding them together, I get a 0, 1, 2, 2. And then on the bottom one, when I subtract row 1, I'm going to get a 0, negative 1, 0, negative 1, 0. And then 2/3 minus 2 is a negative 1 1/3, negative 4/3. Okay, so I was hoping that it was going to be simple. Looks like I'm going to have to do one more matrix to get to where we can get the solution. So I need this guy to be a 0, so I'm going to do a row 3 plus row 2. That should take care of it. I'll get a 0 here. So row 1 and 2 stay the same. Row 2 is the same. So now I'm going to add up the bottom 2 rows to get a 0, 0, 2. And then 2 minus 4/3 is 2/3. So if you plug it in, well, that tells you, the bottom row tells you that C would be, 2C would be 2/3, so C would be 1/3. B is going to be equal to 4/3. Just doing back substitution, 1 times B plus 2 times C, but C is a third, gives you 2, forces B to be 4/3, and then, let's see, C is, A is 1/3. Let me make sure I got this right. A is 1/3, B is 4/3, C, yeah, exactly right. So these are the derivation, from the derivation of Simpson's rule. These are extremely important numbers. So just to kind of reiterate, so for A equal negative 1, B equal, or M equals 0, the midpoint, and B equal 1, we get the following. The area is equal to 1/3, that's capital A, times f of negative 1, plus 4/3 f of 0, plus 1/3 f of 1. So 1/3, 4/3, 1/3 comes from those coefficients that we just solved for. Negative 1 is the left endpoint A, positive 1 is the right endpoint B, and 0 is the midpoint of the two. So I'm going to squeeze one more thing in, more generally. Suppose we're not going from negative 1 to 1 with 0 being the midpoint. The area and here's the formula we got to remember, is h, which is simply b minus a, the width of the interval, times 1/3 f of negative h plus 4/3 f of 0 plus 1/3 f of positive h. This is a more usable Simpson's rule. The 1/3, 4/3, 1/3 rule.